Okay, can everybody hear me? Can everybody hear me? Can someone, can anybody hear me? Distant people, can someone comment?
Yes, we can hear you.
Okay, good, thanks. All right. All right, well, basically, I had an announcement for the other students. I sent out an email regarding people who've been affected by COVID or other things because of the weird nature of this semester that are either have a bad grade and need to take Gen Chem 2 in the spring and don't want to have to wait till the fall to do it. There is an option for those in the situation. I sent everyone an email from the department chair, and he asked you to respond directly to him, copying me to find out how many people want to do this. But it's 5 weeks over the break, 2 hours per day, where you take a new final exam when you return, and basically that replaces, that goes in as the final grade for your class. You get an incomplete essentially, but the requirements are you need to take the fourth test and the final exam, and you decide whether you want to stick with that grade because some students will want to anyway, and others won't. So it's just an option for those that want to do it, but it requires a significant time expense, 2 hours per day during your 5 weeks off. And so it's a situation where please take it very seriously. If you're in that category, I recommend that you read that carefully and then talk to Dr. Ott or email him and ask him specifically any questions you have, because this is the department thing, because other students in the other lectures have had similar difficulties that some of you have. So basically, I hope that addresses some of your concerns. Are there any questions before I start the lecture today? I already asked people here. Okay, let me continue where we left off. Okay, I'm going to start with this one here. Okay, let me share the screen. Can everybody see the screen? Can everybody see the screen? For the
Yes.
PowerPoint? Okay, good. All right, so let's continue where we left off from the other one. As I referred to, the other PowerPoints were very good here, but now I'm just going to review part of it and then move on and finish off the chapter using this one. And the intermolecular forces that are at the end of our book, in the end of that, essentially, those intermolecular forces will come up a little bit in the gas law part, as well as in liquids and solids, and they're better covered there anyway. So that is. So how do we predict the hybridization of the central atom? Well, the first thing you do is you draw the Lewis structure of the molecule, okay? And that's the first thing you do there. Count the number of lone pairs and the number of bonds atoms bonded to it, and then figure out what the hybridization is. If there's 2 lone pairs and 2 bonded atoms, okay, lone pairs plus bonded atoms equals 2, the hybridization is sp. Okay, so basically, if you have a thing with say, for example, example up there, BeCl2, it looks like this. And let me put the pen on here so I can show you. But basically, you have the You have the BE here, and then the CL over here with the dots around it, and then the CL over here with the dots around that. And they're two bonded atoms, so the total is 2 there. Okay? What happens if we go to the next one, boron? What happens to boron? I'm going to erase that. What happens to boron? What's the difference there? What? Yeah, one more, and basically you'll get one more dot here, okay? And so basically you'll have 3 bonded atoms for that one. So essentially that will be sp2. And so boron trifluoride or chloride works there. Does everybody see how that works? So basically they're sp and sp2 based on the fact that the other p orbital is empty. Because with boron, you have 3 p orbitals, right? And they're equivalent, and you only have 1 in them. And then you have the other one down here with 2 in it. One of these shifts up there like that, and these kind of all fit into what is sp2. Does everybody see that? They kind of hybridize like I was showing in the other slides. If you have 4, then it's sp3, and essentially those are the different examples. And of course, ammonia is 1 because it has electron pair at the top, as well as water has 2.
Dr. Douglas.
Yes.
How is BeCl2? How is that only an sp hybridization? Because like there's more than like there's a lot of lone pairs, and then there's 1 bonded atom.
No, with BeCl2, there's only lone pairs on the chlorine.
Oh, so it only matters with the
right.
Central atom?
Right, the central atom.
Okay.
Okay, so notice that nothing there and nothing there, right? So that's what keeps it in a linear form too. So SPs are always linear. So there's a connection there as well. Yeah. So BE, sorry. Yeah.
Is that full?
What?
Is the valence shell full?
No, it's empty.
It has 4 electrons.
Yeah, essentially it's empty because you have 1 S2 like this, and then one there, and then it shifts. One of these goes up like that, and you get the SP hybrid. This is the SP hybrid that's changed. Because remember, each of these P are equivalent. So it's like they could go anywhere in those P orbitals. So it's an SP hybrid. And in the examples in the book will show this. sp3d, some examples there. PCl5 is 1. And basically that would involve the d orbital. And we'll show that how that works. But I showed that also with the other slides yesterday. And then with the next one was 6, sp3d2, and you have sf6 there for this. And the different hybrids look like this with different examples. Now, what kind of thing am I going to ask?
Will you go back for 1 second, Dr. Douglas?
Yes.
Will you go back for 1 second, please?
Yeah.
Okay, I'm good. I just needed 1 last note.
Okay, and now this one, what's a typical question I may ask you on the exam compared to what I did with the last one? Guess, please. Yeah, but what do you think? Like 1 question. What am I gonna put on it?
What's the hybridization?
Yeah, or draw the structures. Draw the structures, 2 points each, just like I did before. Okay.
Those structures, the shape of them.
Yeah, it's good to have them in your head with the colored things, those colored things, and know what they are. So that would be 8 points to draw 4 of them. Okay.
Do we need to draw like the loads, or should we draw?
Yeah, whatever. But I'm not going to be an art critic.
Should we just draw the bonds as well?
Yeah, no, I'd like you to do the lobes just so you get don't do it flat with the Lewis dot structure. Try and draw the lobes if I do that. I haven't wrote up the test yet, but that's the kind of thing I'll put on the exam. That's the kind of thing that's important because it'll help you understand how this is important for organic chemistry, as well as inorganic for complexing of stuff. So it is kind of important. Now, hybridization of carbon, sp2 hybridization of carbon. This is something that's very, very, very important regarding understanding this. Essentially, this is sp2 hybridization of carbon with this. With the hybrid state, you have an sp2 orbital like this, and then one pure p. What does a pure p look like? What's the pure p look like? It'll be like this, okay, like that. Okay, so it's available to form a double bond. An example of something like that would be a structure like this. See, like here. This is sp2, and I'll show you why, okay? This carbon has been promoted. It now has sp3 there, but one is reserved for the extra lobe, okay? So these shift and are now the same energy. So essentially you have the hydrogen over here, you have the hydrogen over here, then you have an oxygen here with one dot there and one dot there. And this is the elevated P. This is the P dot right there. I'm putting an arrow so you can see that. And it looks like this, and this one looks like this with it down. So the result is you've got essentially this lobe going up with this and then forming a lobe on the top and on the bottom for this, forming the pi bond that I described before. So you have a sigma bond and the pi bond in that system. That is sp2 hybrid. Okay?
What's the difference between the promotion of electrons and the sp2 hybridization?
Well, because one of these, this one here, I'm circling it, Brandon. Here, this one here is going to remain a pure P to form the double bond in this structure. It has to be a p orbital. It will not be able to things because there aren't enough atoms to form the other thing. This is with the CH2O example. Yes.
You said the photons like are on top of each other, stacked.
Yeah, up and up. So basically, it would look like this. See, double bond would have the sigma bond in here, and then the pi bond up above and below, and then the oxygen over here. So essentially, what you have. This is why it is trigonal planar and kept flat because of those things above and below, which essentially flatten out the whole thing and keep it flat and keep the hydrogens at that place. And remember, one thing you're going to learn when we get to energy later, essentially energy causes molecules to vibrate and even break apart if they're high enough. And the key thing is the vibrating molecules will cause them to fall apart and be less stable. But the point is this can't vibrate as much because it has a double bond attached very well to the carbon and the oxygen. Okay, so here, the unhybridized orbital gray, which is perpendicular to it, then bonds with another one. So basically they have an example of ethylene like this. And if you were to draw ethylene, you have, this is C2H4, you put the carbon there and the carbon there, and then you have H there, H there, H there, and H there. Here you have one dot like that and one dot like that. What's going to happen with those dots? Well, these are the bonds that form. And so the result looks like this with the dot, 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 and then the carbon here, carbon there, dot, 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 no, line there, and then this bond, the sigma, and then the pi bond above and below, just like that, because these lobes on the top merge with each other.
Why wouldn't it just be a double bond? I don't understand the pi
It is a
bond.
double bond
Well, what's the pi bond?
right there. Yes, or triple. Because the pi bond is a combination of two p orbitals, and they have to be pure p orbitals. This is a pi bond. Pi bond. This is a sigma bond in between. Brandon, did I answer your question? That next picture? My art didn't do it justice.
Not really. I still just don't understand the
But
pi bonds or sigma bonds.
The pi bond is here, okay? Do you see these two things here, this one and that one, merging to form the other one? Let me erase what's on the slide and do it again. If you have a bond, if you have a p orbital looks like that and one that looks like that, what's going to happen when you merge them together? Consider they're like silly putty. You just bring them close to one another. What can happen? What's going to happen to these lobes on the top and the bottom? What are they going to do? They'll merge, and you get this thing up above and below. That's the pi bond. The whole thing is the pi bond, and the electrons kind of shift around. But remember, you always have the sigma in the middle, and electrons don't matter. The whole point is it's a much more stable bond, and that's a double bond. And a triple is even more. Did that answer your question better, Brandon?
I'm still kind of confused, but that's okay.
Well, just read the text. It'll come clear, and then working a few problems will help you too. Yes, Paige.
Are two p orbitals together one pi bond or
There'll be one, and then if you have two p orbitals from both, you'll get a triple bond, and I'll show that in a minute. Because remember, the other p orbital that can do that, it goes back behind and then in front. Okay, and that will merge with it going back behind this and then in front. Okay,
and why is there a sigma bond?
because there's always a sigma bond between the atoms.
Okay.
That's the sigma. The sigma bond is when you have this, the S plus S, like that, or the S plus the P, which would be that side one. This is a sigma also. Those are both sigma bonds. Okay, and the S with the other P will form an SP hybrid orbital.
And if there's a pi bond, there's also
Yeah, there will always be a sigma bond. And you will see that on the quiz / worksheet I'll email it to everybody today, and I want you to work on it for Monday and be prepared with questions. I'm not gonna give credit for it. It's just something to work on. Yes, along with problems in the back of the chapter. Yes.
So based by the illustration, obviously I see that the sigma's in the middle, and then
Right.
there's a pi.
See, this is the sigma here between those. See, that's the sigma,
I
okay?
see that.
And this is the pi.
And then there's two pi circles. Does that indicate just one?
Yeah,
electron?
one orbital, because this is one, this is,
No, I'm talking about the one below it. The drawing below it, it has
Here?
two pi symbols. Yeah, that one. and there's
yeah,
two
because
pi.
these are them both merging like I showed you.
Okay.
But because the
But that
electrons,
stands for one. That stands for one.
yeah,
Okay.
and the electrons, even with the pi's, remember, they're all the same, so they'll kind of migrate. This is just a model that kind of represents why a double bond is more strong
Okay,
and
so
tighter.
I'm assuming each of those pi symbols stand for one electron. Then dividing. Does that make sense?
Well, two for both of them,
Okay.
because you'll have one electron up here and another one down there,
That's what I meant.
wanting to stay apart.
Yes.
And here you'll have two in this thing, but they will all rotate around anyway because electrons are electrons. There's no difference between them.
That's all.
It's like a big cloud around it. It's like a cloud that looks like a kind of like a, it's not a bond because that's a triple bond. That's even more.
Yeah.
Okay, and I'll get to that next. Okay, so basically the sigma bond is the electron density between the two atoms. That's the sigma bond there. And the pi bond is above and below the plane of those. And the pi bonds are only formed with pure p orbitals. Yes.
well, I was just had a question on the worksheet. So which one are you doing in place of our quiz? Which worksheet?
No, I'm not grading this next worksheet. It's just something you work on the weekend, so you could come back with questions
Okay.
or email
I
me
just
questions.
remember in the email you said-
It's just a sample quiz I would give in a normal semester, but this isn't a normal semester. Half of people are virtual and I can't do it. Okay? And I'm just using old quizzes that I've done before that have been useful, that help the students think. Okay? We're just not grading it this time. I graded the last one, gave everybody 20 points, so who completed it. Okay, now another view of this. See the lobe above and below.
Will you go back for 2 seconds and kind of explain the pi bond like definition more?
It's the electron above and below. It's when you merge these two p orbitals together. That is a pi bond. P plus p goes to this. This is a pi bond. Okay. The description alone is not enough to really understand it fully. Do you see the combination there, Brandon?
Yes.
Okay. And you'll get more out of the reading too. Now, another view of this is why it's kept flat. You see that? The pi bond essentially enables it to stay flat. And so in a bigger structure, it'll look like this. What are the red regions? Yeah, but are they more positive or negative? No, in this case, it'll be negative. Unfortunately, they switch the colors on you. But in this case, they're negative because these are electrons above and below. So these will be like the negative regions here, negative, negative, and then this will be positive around the hydrogens. Okay. So there is an aspect of polarity there too, but all the things cancel out because the things go in there will cancel out each other. So that's considered a nonpolar molecule because it's symmetrical and all the things cancel out. Now, along that line, is this polar? That's a similar structure. The only difference is here you got an O. Is that polar? Yes, because the oxygen is more electronegative, and so this will be, the dipole will be directed in that direction.
How can you tell something is polar or not?
But whether it's symmetrical and whether one of the pi poles is negative and positive or a difference in electronegativity. And you could review going back to what I covered yesterday and the time before in the video. I'll be glad to help you with more of that, but it might be just better to also just go back in the chapter a little bit and read that section a little bit more. Does my initial explanation give you enough there, Brandon, to know where to go for it?
Yes.
Okay. Okay, so SP hybridization. Now, what's required for SP hybridization? Well, this you have to have pure thing. Essentially, this will shift to there, and you have to have these two reserved. Okay, and so the ones that hybridize are these things. That becomes now SP, S1, P1 there, and this is now a hybrid form. But remember, these are reserved when you have one up like that, and then and the other one would be back in the back and then out in front. So those are pure P. They're essentially reserved, and so basically you get the promotion electron first like that. The SPs is hybrids, and then you got the PY and the PZ. And basically a structure like this would be acetylene. Now let's do the electron dot structure for that. Acetylene, you put the carbons down first. 1, 2, 3, 4. What bond do you form first there between the carbons? What's it called? The sigma bond, very good. And you have two hydrogens. Be logical, put them on either end. Okay, now this is what?
Those are sigma bonds as well.
Yes. Okay, and now you have a pure P orbital there, and you have another pure P orbital going back behind. Here you got another vertical P4 and then another one going back behind, and they will then form this will form a bond and that'll form another one. The resulting structure looks like this. That is acetylene. That's what you did for the Lewis dot structure. Okay, now I'm going to get rid of my bad art here. And you can see the graphics, how that works. See, you got the two PZs line up along with the Ys line up, and you get the combination looks like that, and it's like a hot dog in a bun, where you got the pi orbitals around it. And so why would that be linear? Why is this linear? Yeah, and essentially it's kept linear because the pi bonds hold it in place. Much like the hot dog is kept linear or the sausage kept linear in the bun because things, even if it's crooked when you put it in, okay?
Why?
Huh?
So why are there 4 pi bonds?
No, there's only 2. There are 4 pi electrons.
Why is there 2 instead of 3 since it's a triple bond?
Because if you look at the structure again with this, the hydrogen here, 1, 2, 3, then the other one here, you form the sigma bond first there. Then you have these 2 that form one of the pi bonds. These form the other pi bond. So now you have a structure that looks like this. How many sigma and pi bonds are in that structure? No. How many sigma bonds are in the structure? 3. How many pi bonds? 2. Okay, and they're the merging of this merges with this one, and this merges with that one, giving that structure down there. And another view of it looks like this, with everything surrounding it kept in like a donut shape, no, a hot dog and bun shape, where the hot dog is this pi bond in between.
How can you tell the amount of sigma bonds?
Count them. Count the sigma bonds there, Brendan.
No,
Look
but
at the carbon
what-
hydrogen, that's 1. The carbon hydrogen, that's 1, isn't it?
Okay, so it's just the central atom to the side
1,
atom.
yeah, 1, 2, 3. So the 3 sigmas, right? How many pi's?
There's 2 pi's, but
Yeah,
where did you get
2
the 3
pi's.
sigmas?
3 sigmas, 2 pi's. So 3 sigmas, 2 pi's. And again, 1, 2, 3 of the sigmas, and then you got 2 pi's. And remember, each pi has a lobe above and below. Okay, because those electrons want to stay far apart from one another as possible. And that's what it looks like. Now describe the bonding with this one. I just did that for you earlier. And you can see there with the 3 bonded atoms, 2 lone pairs, that would be sp2, and it looks like that. And I already put that also on my earlier slide, but that is with their better art. And frankly, I love the art in some of these PowerPoints. It's like the people that put these together, they're artists regarding the graphics, and I'm not that kind of person. My wife is, but I'm not. Yes, you had a question. Nick, you had a question?
The first sigma bond, the first bond is always a sigma bond.
Correct. So how many sigmas are going to be there?
3.
3 and 1 pi. Okay.
The lone pairs on the oxygen that charge for accepting bonds,
No, it'll make a lobe like these there.
but it doesn't make a single
No.
pi.
And again, if you look at it, another one with this, the sigma and pi bonds, with there, a double bond, every single bond is a sigma bond, every double bond is a sigma and pi bond, every triple bond has a sigma and 2 pi bonds. So essentially all of them have 1 sigma. That has to start with it first. Now, if I go back on the slide and put in on this slide here, if I put CO2 here, what's the nature of CO2? You have oxygen over here with 6, right? And then another oxygen over here with 6. Okay, you form a bond there, a sigma there. How many pi bonds will there be? 2. 1 will be here, okay? 1 will be there, and then this will form there, and essentially this is an sp hybrid because you have to have those pure p's. They're just at different angles, and they don't give them in these slides, but essentially this would be above and below, and this would be back behind and in front. And they kind of merge between each other, so it's like you get a little less dense bun around the hot dog between them, but this is also linear for the same reasons.
That's what it says where it has like single bond.
here.
No, the one that had a lot of work. Yeah, like one. I think it's one past one.
Here?
No, it said single bond, double bond, triple bond, and it said the types of bonds.
Oh, okay, it's the other way. And again, the sigma can look like this. It can be the combination of this plus this goes to form this structure. Okay? Or it can be this plus this goes plus this goes to form this structure. Or it could go to an S plus a P that's flat like that and essentially forms a bigger structure with a little lobe over there. And those are all sigma bonds. Those are the three kinds of sigma bonds that can occur. The pi bonds are only like this plus like that, and then you get the lobes on the top and the bottom or behind and in front.
So in a triple bond, will there always just be one sigma bond?
Yes. And two pi's. Now let's look at an example. How many sigma and pi bonds are there in acetic acid? Well, let's draw it first. And I'm just to save time, I'm just going to do it myself, but you can do it yourself for less time. But this is what it looks like here, and then you have the CH here like this, like that, and like this. So how do you figure out how many sigma and pi bonds there are? You just count them. So how many sigmas are? Let's go through this left to right. How many sigmas are there?
7.
Yeah, 1, 2, 3, 4, 5, 6, 7. 7 sigmas. How many pi's? 1. Very good. Okay, and the 1 comes from the double bond there on the oxygen. I'll get rid of that art there. Yes.
On the test, would a question that you would ask be something similar, like, here's a picture, like how many sigma bonds?
Yeah.
Like that could be a question.
Or I give you that, or I give you this, and then say how many sigmas and pi's, and you got to draw it out.
Okay.
So that's why you're doing Lewis dot structures. That's why you've been doing it all along. It just fits together nicely. So you're thinking like a chemist. Good for you. And biologists have to do that. Okay, so that's what I've tried to train all of you to do here. And it's hard. It's hard to learn a different way of thinking because it's under the concept of critical thinking. It's like you're putting pieces together using all sorts of information. And there's people that get very, very good at it. And as I've gotten more educated, the more I realize how much I don't know. And there's some really brilliant people who can communicate it better, whatever. And I find my eldest son, it's like I'm totally overwhelmed as his area of his own smartness in that area. But that's his gift. You all have your own. So it's a situation where basically it's just a matter of appreciating the way God made you, okay? So basically you have pi bonds associated with this. How many sigma bonds are with this one? 1. How many pi's? 1. Okay. So this would be called diamagnetic here, paramagnetic and diamagnetic. Molecular orbital theory is the next part of the thing. And basically I will just introduce that to you here. And paramagnetic and diamagnetic is discussed in your textbook, and I'm not sure where it is in the text. We're not going to really get to that, but molecular orbital theory, bonding orbitals, whatever, I'll just touch on briefly. Yes, you had a question.
I understand that double bond has 1 sigma and 1 pi, but on the last one, when the carbon was bonded, or double bond to the oxygen, was that not a sigma 2 with that?
Yeah.
It was. So
Here, if you got this with that, it's the same thing. They're 2 sigmas and 2 pi's. Yeah, and basically oxygen, paramagnetic and diamagnetic is discussed in your book a little bit.
But you don't, we don't.
No, because that's more, no, I'm not going to concentrate it with this. It changes the subject a little, and I don't want to do that. There's another aspect called molecular orbital theory that I'm just going to address briefly here. Energy levels of bonding and anti-bonding orbitals in hydrogen. And for example, if you have a hydrogen like this, its structure will look like this. And then you bring in another hydrogen next to it like this that has a structure that looks like that. They merge to form a lower energy that would look like this with one up and one down. And remember, when you bring them close to one another, they give off energy, okay? And then the upper one, like this, is considered, this is empty. And essentially, this is called the anti-bonding orbital. And this is addressed briefly in your book. They're anti-bonding and bonding orbitals in each of the different kinds of bonds. When you get a bond, it has to do with you have more bonding orbitals than anti-bonding. And I'll illustrate that to why you cannot get He squared. It will not work. They will repel each other, okay? And so that's what this part is essentially talking about. But I encourage you to read this part of the chapter to understand this a little bit more. But let's introduce it to you first. We have it. This is what the energies look like with the hydrogen. Okay, and when they merge, they form a lower energy. Why do they form a lower energy? Because energy is given off when that bond happens. It requires energy to break it, right? So it's going to give off energy when it forms. Okay, and so it will go to a lower energy here. The mixture of those, and then you'll have the hydrogen bonded to the hydrogen on the other part. What about helium? How many electrons does that have? 2. So one of them is going to go up here and one down there. And so basically they'll be repelling each other when you do that. And this is called constructive interference with this ball and this ball coming together, and you get a sigma orbital. And this is where the sigma and pi's come from. You get this sigma orbital relationship between them both. And that's the nature of the sigma bonds. You get the sigma kind of orbit. And a bonding molecular orbital has a lower energy than the higher one. And this will be addressed more the first chapter of General Chemistry 2, where we talk about energy. And this is sort of the way this book does it. They do it as an introduction to it first. I much prefer to have energy taught for the second exam, after you finish chapter 4, but the department does it a different way with this book. They have their reasons, which is fine, but basically I just prefer it the other way. But again, different books do it in different order, and it's just what people are happy with. Okay, destructive interference is an anti-bonding one. And why would there be destructive interference? Well, it's because they don't have space for extra electrons. They're unable to share. If you have an He like this and another He like that, can it bond with anything according to the Lewis dot structure things we did before? Can it bond? No, there are no open things available. So if one helium gets close to the other one, that's one reason it's a gas. They'll bounce off. There's no intermolecular forces between them because those electron clouds will repel each other. That's what the anti-bonding essentially means. That when you have things in the anti-bonding thing, you do not have the there. And an anti-bonding molecular orbital is higher energy and lower stability, and basically it will repel each atom from each other. In other words, it will make the bond length larger. Okay, so constructive and destructive interference, you'll learn this in physics. If you have constructive interference when they come together like this, you get the sum of the waves, and then destructive interference like that, you essentially get nothing. And in this case, it would be like helium together with helium there, and this will be one ball, and that'll be one ball, and they will stay away from me. They will bounce off each other. They will not stick together. If you had an individual hydrogen atom come next to another individual atom, if they come close to each other, what's going to happen to them? They'll bond. That's because that's a lower energy part. Okay?
He2 is not possible.
No. Now let's look at two equivalent p orbitals. Okay, and an example of that would be using p orbitals associated with this. So when you have p orbitals associated with this, say for example, you have a boron here that has 3 and another one, and a boron here like this. Would this indicate that that is theoretically possible to get boron 2? Sure, okay. But in that case, it is the p orbitals interacting with this, forming this little bond. Okay, but practically it doesn't exist because the boron likes to do BH3 or something. But practically it doesn't exist. It's not stable because it would be way too reactive. It much prefers to be an sp2 form instead of just merging that way. But theoretical, it is possible. Now, how many of you like to watch Star Trek? Well, one of the things that was funny with that would be dilithium crystals. Is dilithium possible? Sure, why not? But it's a metal, and so it's not really costly, it's just lithium metal. So dilithium crystals kind of is silly, but theoretically it's possible, but real life and theory often doesn't mix. So it's just funny that when I started taking chemistry in college, and I liked watching, in 1975 through 79, I watched reruns almost all the time of the original Star Trek series, and it always made me laugh, the dilithium crystals. Dilithium stockpiles, they took it out of the ground and everything. So in any case, the possible interactions between the p orbitals there, you can have constructive and destructive interference. And this is what this looks like with this slide. Look at the constructive interference between the two p orbitals. Well, this is the little lobe at the bottom, and then big one in the middle, and then the little lobe over here. That's the constructive interference. That's the sigma bond there. Okay, that would be the same between, for example, you have a methyl over here, and you have another one over here with this. This would be this bond here. And this is what that would look like between these two p orbital things interacting in this way, and you get this kind of structure. Okay, and destructive interference there, things there, if you have destructive constructive versus destructive, you'll get a pi orbital here with that, and with that, there isn't one. General molecular orbital theory for the second period ones, essentially you just fill in the boxes and see how they go up. So basically you can get lithium, beryllium, whatever else going up through these boxes. And what I'd like you to do over the weekend is take this slide and try and fill it in for yourself and tell me whether that bonds or not. Now, what do I mean by that? What would you do for the lithium ones? The lithium is the 2s1, so it's not really there, but this, and that, and you can do that. But you'll find with nitrogen, you get a triple bond in the middle. And so basically you got all these filled in here between all this, the 6 electrons get all put in here. There's nothing there. So you have the triple bond, and you have one sigma and 2 pi's for that. So that's essentially the nature of that. Now, molecular orbital configurations, basically they can accommodate there. And the bond order, if you were to do the bond order with this, and I'm not going to get into bond order at all in this class, but this is a sample chart. And I might have a question on the test about this, but I decided not really to, I don't think I will on this thing, but just talk about bond order in general, what it is. Like with a single bond, the bond order is 1. A double bond, what is the bond order? 2. Triple bond, what is the bond order? 3. Okay, keep it simple. And then delocalized things there where you extend over them, and that has to do with the resonance forms. When you have benzene, you can have 2 different resonance forms with benzene. What's the other resonance form? What's the other resonance form going to be? The other one will be like this. You do this like that. Okay, and you have double bond there, double bond there. So you get the combination of both. And so the resulting structure looks like this. And when you take organic, you'll learn to practice that. But that circle indicates this above and below with the delocalized pi orbitals going around and everything kind of sharing there. And essentially, how many sigma bonds do you have with that structure? Yep. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. How many pi bonds? 3, but they shift. Okay. And then you get the bend thing above and below, and carbonate kind of looks the same because you've got resonance forms then, and then you got a buckyball or graphite, and that ends the slides. Any questions? Okay, we're done for the day. We are done the chapter. I encourage you to read the end of the chapter in our book just to get an introduction to intermolecular forces, but I addressed it briefly in today's class. Yes?
What chapters is the text in?
Chapters 8 and 10, I believe. I'm going to Gauss laws on Monday.
And this is chapter 8.
Yes. But in the slides, it's chapter 10 for Chang. Those of you who are distant, any questions? Okay, we're done for the day. I'll see you all on